Okay, so I will be talking about the recent paper. This wants to move, yes, that appeared 1 month ago. So you see my hand, no? Okay, that appeared 1 month ago in the archive with Daniel Aloni, Matt Rees, and Moto Suzuki. So Matt gave a talk last week at the Symmetry seminar, and he did actually an amazing job at explaining all the swampland motivations to think about -1 form symmetries. So I will mention this, but I will not be as exhaustive as Matt, unfortunately. But I think his seminar was very good. So it's on YouTube if you want to check it. I will start with a review of higher form global symmetries. Probably you've heard this many times, but I will do it again. And then I will use a definition of -1 form U1 symmetry, which is a notion that has appeared in the literature, but I will give a definition to know what we are thinking about. And I will comment on its properties, and I will compare it to higher form global symmetries to see that it shares some of the properties, but it doesn't share some of them. I will then go on to describing how we can think about spontaneous breaking of this kind of symmetries. And in particular, I will start with a lower dimensional example, which is 2D abelian gauge theory, and the Schwinger model, which is 2D abelian gauge theory coupled to a massless fermion, which is dual to, I will explain this later. And then I will draw some general lessons from the spontaneous breaking of this in this model to other theories. I will then describe how S-UN Yang-Mills and physical QCD have a -1 form symmetry, which is the instantonic symmetry, which one can see that it's spontaneously broken in the same sense as it is spontaneously broken in 2D Maxwell theory. And I will connect this fact to an open problem in phenomenology, which is the strong CP problem. And then I will finish by looking at the strong CP problem solutions that are in the literature and reinterpreting them from our point of view. And then I will try some attempts at finding new solutions to the strong CP problem, but these attempts are so far unsuccessful. Okay, so let me start with the review. So usual U1 symmetries, zero form symmetries, are characterized by a conserved current, which is one form, and this is the conservation equation. One can exponentiate this current to find a charge. Sorry, one can integrate this current to find a charge, and then if one exponentiates it, there will be some symmetry operators which are topological by the conservation equation, and they depend on a parameter alpha that takes values on the circle. And then one can, well, these symmetry operators act on states, but one can use this notion to define an action on local operators. So symmetry operator acts on a local operator, which here is this little red dot, by linking. And what this means is that if we take some correlation function, which has some local operator O inserted, and we insert a symmetry operator and deform it such that they unlink, there will be some phase, and this gives us selection rules. Okay, so this is the usual story of the normal zero form symmetries. This can be straightforwardly generalized to higher form symmetries by considering P+1 form currents. This is the conservation equation. One can again exponentiate the integrated current, and this gives us some topological operators, which are again topological because of the conservation equation. Now, the objects that are charged under this symmetry are not local operators, but p-dimensional objects. So for instance, for a one form symmetry, there will be lines that are charged under it. And if we consider some correlation function with one of these lines inserted, we can wiggle a topological operator that links with it to find selection rules. Now, the usual example is U1 gauge theory in 4 dimensions. So this theory has an equation of motion, which is d star f equal to 0, and a Bianchi identity, which is df equal to 0, which can be reinterpreted as conservation equations for two-form currents. So one can define an electric two-form current, which is F, a magnetic two-form current, which is star F, and they are both conserved. We integrate and exponentiate them to find two sets of topological operators. which implement the symmetry. Then the symmetry is U1, 1. So this is a one-form electric symmetry, one-form magnetic symmetry. And the symmetries act on Wilson lines, the electric one, and on Toft lines, the magnetic line, in this way. So this is just the same as the equation I wrote before. So if I unlink the two operators, I obtain a phase. And this gives me some selection rules. Importantly for us, both symmetries are spontaneously broken, as can be seen by computing the vacuum expectation value of the charged operators. So one computes the vacuum expectation value of the Wilson line, and this obeys a perimeter law, which means that it can be made non-vanishing by including a local counter term on the word line. And this is the definition of an spontaneously broken one-form symmetry. So both are spontaneously broken. And in fact, one can argue that the Goldstone boson for this spontaneous breaking is the photon. And this can be seen, for instance, from this equation. Here we insert a photon, and we compute this correlation function. And the result means that the current, the electric current, acts on the vacuum, creates a photon, which propagates a massless excitation. So this is the Goldstone boson, the Goldstone theorem for one-form symmetries. Okay, so this is a well-known story. But I want you to remember that there are two one-form symmetries that are spontaneously broken, and the Goldstone is the photon. Now let me change gears and think about minus one-form symmetry. So minus one-form symmetry in principle can be extracted from the previous definition by taking the case P equal -1. But it's a bit degenerate, so as I'm going to describe now, but let us adopt the following definition for a minus one-form symmetry. We'll say that a theory has a minus one-form U1 symmetry if it contains a local operator, J0, that can be coupled to a background field that takes values in the circle. So this means that I can include this term into the axiom.
Edu,
yes.
Can I ask a quick question?
Yeah, sure. Please.
So, you say that you have any operator J0 that can be coupled to a background field that takes values in a circle. Suppose I have two operators and together they parameterize like a plane, okay? Mm-hmm. Right? Then, I can go to polar coordinates and, get a circle just from the polar coordinates. It's a contractible circle. Does that count for you as minus one from symmetry? Or are you requiring that the circle is non-contractible in some sense?
Yeah, I don't know. I mean, there is a sense in which the circle is not contractible because it parameterizes a circle in parameter space.
But this is also a circle in parameter space, right? Like just take a plane,
right.
Just draw a circle in the plane.
Yes. Yeah, I don't know.
Okay, no, it's fine. So I guess it doesn't matter too much for what you're telling us.
I mean, at this level of the definition is just having this operator that couples. Yeah. So I mean, what one needs is to have at the end of the day, what one needs is to have a top form, if you wish, which is this star J0.
Yeah.
That is quantized. So that's the important property.
Okay, thanks.
All right, so this is written here. So this integral needs to be quantized. This is what ensures that the background field is periodic. And an example that has been discussed previously is that for the non-abelian gauge theories have a minus one form symmetry, whose charge is the instanton number. So this is the current. And then, of course, a background gauge field for the symmetry is a theta term in a non-abelian gauge theory. So this is a usual notion in 5D, and in 4D, one is forced to think about minus one form symmetries. Sorry. So the point of view that I'm going to take is that the minus one form U1 symmetries are features of QFT that share some properties with higher P-form symmetries, but they don't share some other properties. Okay. So let us see which properties they share. Let me just go very briefly over properties of P-form U1 symmetries. So P-form symmetry, we have a conserved current. If it's U1, the current is quantized. Then we can construct these symmetry operators. They will act on charged objects, and moving this topological operator will give me correlation, will give selection rules. We can then, if we have a conserved current, we can couple it to a background gauge field. This means including a term like this in the axiom. the current is conserved. This means that the background gauge field is invariant that this implies that there is a redundancy of the action, which is small gauge transformations. The current is integrally quantized. This means that there is another redundancy, which is large gauge transformations. If the symmetry is not anomalous, it may be gauged. This means that I take the background gauge field A. This is the path integral that depends on the background A, and then I integrate over all possible configurations. So I promote this background field to a field, and the resulting theory doesn't depend on the background. If this cannot be done, the theory is anomalous. The symmetry is anomalous. And typically, an anomaly can be encoded by anomaly inflow. And for the Maxwell theory, for instance, there is a mixed anomaly between the two symmetries that I presented before. Remember, there was an electric one-form symmetry, magnetic one-form symmetry. These are background gauge fields, two-form background gauge fields for these two symmetries, and this encodes a mixed anomaly between the two. This means that if I gauge one of the symmetries, the other will be explicitly broken. Finally, if the charged operator of a symmetry takes a bev, we say that the symmetry is spontaneously broken. And this implies by the Goldstone theorem that there is a massless Goldstone boson. In the case of a zero-form symmetry, which is this equation here, this is a scalar field. In the case of higher p-form symmetry, the Goldstone boson is a p-form gauge field. Very good. What about the minus one form symmetries as we just defined them? The current is a zero form. One can in principle define this, but the problem is that the conservation equation is tautological. So essentially, a star J0 is a top form, which is always closed. So it's not clear that this equation has any meaning. What is still true is that by our definition, the integral of star J0 is an integer. So this is importantly different from the higher p-form symmetries. Relatedly, one can try to define topological symmetry operators, but these operators span all of space-time. So it's not clear that one can insert them in correlation functions to obtain selection rules. Also relatedly, there are no charged operators. So it's not clear so if we just follow the p-form symmetry dictionary, charged objects under minus one form symmetries are dimension minus one. So again, we cannot insert these things in correlation functions, and we cannot get selection rules. At weak coupling, one may say that minus one form symmetries act on instantons, but it's not clear that this notion makes sense at strong coupling. Okay, so these are three things that are not common between higher p-form symmetries and minus one form symmetries. One thing, okay,
so,
and I'm going to say, yes, sorry.
Edu, can I ask you a question? So,
sure, please.
When you basically define, like you said, as U1, if the integral, for instance, for the instanton case, the integral of trace of f squared is an integer, right?
Yes.
That's a semi-classical statement. Is this that statement? If I take any classical gauge field configuration, that integral is an integer.
Yes.
Quantum mechanically, if I'm not just a weak coupling, if I'm a strong coupling, what's the thing I should compute? Is it something like the value of the partition function, and then my question is it obvious that it's still quantized exactly like that? Because you are supposed to sum over instantons, right? It's not like you just get to choose. Yeah.
Well, yeah, that's precisely the reason I wrote that. So I think that's a very good question. I don't really have an extremely sharp answer. That's the reason I write that at weak coupling, one may think they act on instantons. It's not obvious.
Yeah.
Yeah, okay.
Got it, thanks.
Yeah, I think that's a very good point. All right. So one may couple background gauge field. Okay, this is just by our definition. And then the conservation equation is empty, and relatedly, there are no small gauge transformations. There are no exact zero forms, but the current is still quantized, and this implies that there are large gauge transformations. These W0 here are closed, but not exact zero forms. These are just integers. So the large gauge transformations are just shifts of the background gauge field. If the symmetry is not anomalous, it can be gauged. This again just means that we integrate over all possible field configurations for theta, and we learn, okay, we didn't learn, this is well known, a compact scalar field can be thought as a gauge field for a minus one form symmetry. And if this cannot be done, then there is a mixed anomaly. And these were discussed in these two papers. They go under the name of anomalies in the space of coupling constants. And they can also be encapsulated by anomaly inflow. And for instance, in 2D Maxwell, a theory that we will return to in a couple of minutes, there is a mixed anomaly between theta, which is the background gauge field for the -1 for symmetry, and B, which is the background gauge field for a electric one-form symmetry. And of course, the seventh point is the one that I'm most interested about in this talk, which is whether we can talk about the spontaneous breaking. At first, well, it's not clear that this is going to make too much sense at this point because there is no charged operator that can take a bet. I told you that there are no charge operators under -1 form symmetries. And also there is no candidate for a Goldstone boson. So if we just follow the Goldstone, the P-form symmetry dictionary that I wrote before, we would need something like a -1 form gauge field. And I am not sure what this is. But so what we are going to do in this talk is to explore this possibility and try to overcome these two problems. So let me just give you some motivation to study -1 form symmetries, and in particular some motivation that is related to the Swampland program. So we know that there are no global symmetries, or we believe there are no exact global symmetries in quantum gravity. And these -1 form symmetries have been sort of put in a same footing, and the absence of -1 form symmetries has been linked to the absence of free parameters in quantum gravity. I would say this statement has less support than the absence of global symmetries. One cannot do these arguments with black holes and so on, but seems to be true, at least in perturbative string theory. And and there are some comments in this paper related to this statement. And this opens up a possibility to finding phenomenological implications from Swampland conjecture. In particular, as I'm going to also explain now, -1 form symmetries are related to axion physics, but also to models of axion monodromy for inflation or relaxation monodromy for the cosmological constant. So I think this opens up a nice avenue to find the phenomenological implications from a Swampland principle. And I think this is enough motivation, at least for me, to try to understand better what these -1 form symmetries are and what we can say about them. Okay, so these are just some references. So these are these two papers on the anomalies. There are more references in the literature, but I want to highlight these three, and in particular this last one by, several people in the audience. So this paper by by Ben, by Tom, by Miguel, Irene, Matt, and Jake. I hope I didn't forget anyone. It's very important for everything I'm going to say. So, okay. So let me go to spontaneously broken -1 form U1 symmetries. And let me start with the 4D Maxwell theory that I presented before. I told you this theory has two one-form symmetries. They are both spontaneously broken, and the Goldstone is the photon. If we go to 3 dimensions, the story is somewhat similar. There is still an electric one-form symmetry. There is now a magnetic zero-form symmetry. And the electric one-form symmetry is not spontaneously broken. This one can compute explicitly. And the magnetic zero-form symmetry instead is spontaneously broken. And one can understand the photon as the Goldstone for this spontaneously broken zero-form symmetry. And it's a bit, you might be surprised because I'm saying that a zero-form symmetry has a Goldstone, which is a one-form gauge field. But this is fine because in 3 dimensions, the one-form gauge field is dual to a scalar. So the dual photon.
Sorry, I just wanted to quickly ask, like in 11 dimensions, there's like Coleman-Mervin-Wagner theorem that tells you there's no spontaneous. So this case,
right, this is imprecise agreement, right? In 3 dimensions, the Mervin-Wagner-Coleman theorem will tell you that one-form symmetry cannot be spontaneously broken.
Yeah, okay.
But it will tell you that the zero-form symmetry can be.
Okay, thanks.
All right, so again, in 3 dimensions, we can understand the U1 gauge theory as the theory of a Goldstone, which is the photon of a spontaneously broken zero-form symmetry, which is the magnetic symmetry. Okay, this is a well-known story. And now the obvious question is what happens if we go to 2D Maxwell theory. So in 2D, there is still a one-form electric symmetry, but now there is a magnetic minus one-form symmetry. We can see that there is a magnetic one-form symmetry from our definition because we can couple a background field, which is valued in the circle, which is this theta, of this theta term in 2 dimensions, that couples to the magnetic current, which is F. In agreement with what Miguel just said, the electric symmetry is not spontaneously broken. And then the question is whether we can think about 2D Maxwell theory as the theory of an spontaneously broken minus one form symmetry, and in which sense the 2D photon, which doesn't propagate any degree of freedom, can be thought of as a Goldstone field for this spontaneous break. Okay, so
just a quick question. Do you have a Coleman-Merman-Wagner theorem for 1D systems where it would appear that you can't break a U1 minus one form symmetry?
Yeah, that's a very good question. So in order to do the Mervin-Wagner-Coleman theorem, typically you need to assume that there are propagating fields. So in the Coleman paper, for instance, there is you need to say that there are Goldstone bosons that propagate the spontaneously broken symmetry. So I don't know if there can be an argument made in the case of minus one form symmetries. Maybe yes, I don't know. I think it's a good question. So I'm saying the thing about propagating degrees of freedom because as you see in 2D Maxwell, there are no propagating degrees of freedom. So it's not clear in which sense one can do the argument of Coleman. All right, so let me explain the physics of 2D Maxwell theory in a bit more detail. I can put the theory on a circle, and then if I choose appropriate D gauge, I can, the only degree of freedom is this field, and the action on the circle takes this form. So this is just the action of a particle, quantum mechanical action of a particle in a circle. So this field is periodic because of the gauge transformations of A1, and there is a magnetic field which with the strength theta.
So, Edu, a quick question. By putting it on a circle, you're actually reducing it to the case that Ethan was talking about, right? Now this is quantum mechanics.
Yes, this is quantum mechanics, but I am not doing dimensional reduction. This is a true statement. I didn't forget any.
No,
yes.
But
it's a 2D theory.
You put it in a box, right? I could take the size of the box to be very small. The IR properties of this, they are like it was a quantum mechanical model.
Yes, you're probably right.
Okay.
So we can solve this system. It's solved by proposing these eigenstates. So the different states are indexed by an integer L, and the energies take this form. So they depend on L and theta of the different. So I'm going to call this eigenstate just vacua. So the 2D Maxwell on a circle has different states, and they are characterized by a constant electric field in the vacuum. And here I plotted the spectrum. So there is a multi-branched potential for these different Ls. And if you, for instance, sit that theta equals somewhere here, the ground state will be in this first branch, and then there will be some other vacua that lie above. And a further thing that you can do in this theory is to put probe particles that are electrically charged. You are in the circle, so you need to put an even number. If you put 2 probe particles, the electric field will grow between the 2 particles, and this will give rise to a confining force between the 2 particles. So we say that to the electromagnetism is classically confined. Putting 2 particles is the same as putting a Wilson line, and this will be important now. Okay, so this is the physics. In which sense can I say that the minus one for symmetry is spontaneously broken? So what we are going to do is to argue it in an indirect way. So if I gave you some theory with a zero form symmetry, and I didn't allow you to compute any vacuum expectation value or anything, you could try to infer that the symmetry is spontaneously broken by gauging it. If you have some zero form symmetry and you gauge it, you expect to have a Higgs mechanism And if you find the symmetry in the gauged phase to be the Higgs phase, you will conclude that the original symmetry was spontaneously broken. So this is what we are going to do. For a normal symmetry, the Higgs mechanism is associated to the following physics. There will be a gauge boson that eats the would-be Goldstone of the spontaneously broken symmetry phi and becomes massive. This can be described in terms of a Stuckelberg-like coupling. Because the gauge boson A is massive, there will be the electrically charged objects will be screened. And a further fact that happens in Higgs zero-form symmetry is that objects that are magnetically charged under A, so in this case, there will be magnetic monopoles, are confined. So we want to argue that these three things happen if we gauge the -1 form symmetry of Maxwell theory. So we can gauge the -1 form symmetry by introducing a compact scalar field phi, which is the gauge boson for the gauged -1 form symmetry, and we couple it to the magnetic current. If we do this, because remember that the energy of 2D Maxwell theory depended on theta, so it will now also depend on phi. And in particular, there is a potential which depends on phi quadratically, and this gives phi a mass. So phi is the gauge boson for the -1 form symmetry. So this looks like this first palette point here. Then because, well, we can see this in a bit more detail, at least formally by introducing an electromagnetic dual field to A. So in 2 dimensions, this is a bit degenerate. And we need to introduce a field strength N, which is integer valued. So this is just an integer. But we can formally do this. And if we just follow and do electromagnetic duality, we will find a Stuckelberg-like coupling where phi, which is the gauge field now. So here phi, so is the equivalent of A here. Phi, it's eating this field strength. This would be Goldstone, and it's becoming massive. Okay, so phi is massive. This leads to electric screening. So correlation functions containing insertions of this vertex operator with decay at log instances. What about magnetic screening? Magnetic confinement. So we can take phi, which is the Goldstone boson. We can dualize it to this phi tilde electromagnetically. And we'll find, again, a Stuckelberg-like coupling by which phi tilde is eaten by A. And what we can infer from this coupling is that phi tilde needs to transform under the gauge transformations of A. So importantly for us, what this means is that the magnetic vortex operator, which is the object that is magnetically charged under the original phi, is not gauge invariant. And we need to attach a Wilson line. So the object that is gauge invariant is this guy that has two vortices attached to a Wilson line, where the boundary of gamma is these 2 points. And I told you that Wilson line gives rise to a confining force in 2 dimensions. So what this means is that these magnetic vortices are classically confined. So again, we find magnetic confinement. So we conclude, because all these 3 properties are satisfied, that the -1 form G1 symmetry in the...
One quick question. Shouldn't we expect like some minus, for example, in the phi at x2? So like when you put them together, you...
So, right. So, well, where, sorry, a minus? Well, I guess this is just a matter of orientation. I don't know. Why do you want a minus?
Orientation, they've chosen phi tilde. I think you need a minus.
I didn't hear that.
Don't you need a minus sign? It's just like core anti-core.
Let's see. Well, I guess maybe I should put, I guess, there should be a minus, yes. Yes. Yes, there should be a minus. Okay, in any case, the bottom line is the same. Magnetic vortices are confined, And this means that the gauge symmetry is in the Higgs space. And what we interpret this to mean is that in the original theory, where the symmetry was engaged, the global -1 symmetry was spontaneously broken. All right, so we argue that the symmetry is spontaneously broken, but we don't really have an order parameter so far. What we do have is that we noticed that a quantity that was very important in having the Higgs effect is the vacuum energy. So if the vacuum energy didn't depend on theta, on the original theory, then phi would have been massless. So the potential wouldn't have depended on phi. And the gauge -1 from symmetry wouldn't be Higgs. And therefore, the global -1 from symmetry, the original global symmetry, wouldn't be spontaneously broken. So based on this fact, we propose that the spontaneous... sorry.
So do you want the energy to be independent of theta or to not have like a quadratic part? If it has like higher order, would you still call it?
Yeah, we would still call that spontaneous breaking. Yeah, I think that's a good question. So I would say that that's still spontaneous breaking, but I don't know any theory that has that behavior. That has a dependence on theta, but has second derivatives to 0.
I think you can get more general potentials by taking a non-canonical kinetic term for the top 4.
Right. Yeah, more general potential. Yeah, but I think the question is whether if chi vanishes, but there are other. So the energy still depends on theta, but second something that's like linear on theta. Yes. Well, I don't know. I don't have a theory that has this behavior, so I don't know what to think about it.
Thanks.
Yeah, I am not sure that's possible. Okay.
Maybe it's not. Yeah, because theta is like a 2 pi periodic thing. So if it has like a higher order, like it's hard to think how you can have something that is periodic but doesn't have like a quadratic part. It's a little weird. Maybe it's like sine of theta or something like that, but still it's sort of like linear around the origin. So it's kind of, anyway, yeah, it's kind of tricky. Thanks.
Yeah. No, but yeah, that's a good question. That's a question we actually thought about at some point. So I think, but since we couldn't come up with a theory, yeah, okay. Yeah, I don't. In any case, at this stage, what we do is to propose that the spontaneous breaking of the -1 from symmetry can be diagnosed by the explicit dependence of the vacuum energy on a constant background electric theta. And in particular, the leading measure of such dependence is the topological susceptibility. Okay. Which is what Diego was asking about. So we take the topological susceptibility to be effectively as an order parameter for the breaking of this -1 from symmetry. And an interesting fact, so we argued that this is an order parameter, but we didn't make any connection with a Goldstone boson or a would-be Goldstone. We didn't make any connection to the 2D photon. Something that is quite suggestive is that chi, so this is the definition in terms of the vacuum energy, but it can be rewritten in terms of this not gauge invariant 2-point function. So this is a 2-point function which is not gauge invariant, but this integrated correlator, the limit q equal to 0, is explicitly gauge invariant. And if chi is different from 0, what this expression implies is that this integrated 2-point function must have a pole at q equals 0, a quadratic pole. And this sometimes is called the Kogut-Susskind pole. And this looks a lot like a Goldstone theorem. So we have an order parameter, and if this, so in the usual Goldstone theorem, you typically have some 2-point function, and you have an order parameter. And if the order parameter is non-zero, then the 2-point function must have a pole, which is the pole associated to the Goldstone theorem. So in this case, what we have is some order parameter, and if it is non-zero, there has to be a pole, but the pole is the funny Kogut-Susskind pole, which is not associated to any propagating degree of freedom, but is rather associated to the masslessness of the 2D photon. So this is the closest we got to a Goldstone theorem. And
sorry, can you go back to the? I have
yes.
a quick question. So when you evaluate chi, you take the second derivative and then you set theta to 0, or do you leave theta arbitrary?
No, I just set theta to 0. Yeah, sorry, I forgot to write this.
How about if chi is 0, but the theta is not 0?
Right, yeah, this was Diego's question.
Because of periodicity, you're not allowing that? Is that what you're saying?
Sorry?
You're not allowing that because of periodicity?
Yeah, I don't know if there is some theory with that property. Let's say this, for us, the natural quantity is the topological susceptibility, because it's the one that is giving the mass to the would-be Goldstone to the gauge field. If there is a theory that has chi 0 and still a dependence on theta, this would be sort of a problem for our reasoning, I would say. But I don't have an example. I don't know if it's a problem, but something that I would like to understand better, but I don't have such a theory, so I don't know. I don't have more to say.
So just to make sure I understand this, at least the philosophy, you're saying if chi is not 0, you would say that your -1 form symmetry is broken, and that's related to a masslessness, not massing up of something.
Right. So the theory that I'm
that's out of the Goldstone boson for you. Is that what you're trying to say? What are you trying to say?
Right. Okay. Yes. Sorry. So let me rephrase it. So we had this -1 form symmetry, this U1 -1 form symmetry. We argue that it's spontaneously broken, and that the order parameter is chi. And the Goldstone boson is the photon. So remember that we are talking about this 2D gauge theory. So we want the 2D photon, which is massless but doesn't propagate any degree of freedom, to be the Goldstone of the spontaneously broken -1 form symmetry.
And you're saying that if you gauged it, then that becomes massive. That gauge field becomes massive, becomes fixed.
So if I gauge the -1 form symmetry, the gauge. So this Goldstone
that should be eaten up, right? I'm just trying to understand.
Yes, it is massive. You can see it. So it gets a mass by eating the dual field.
I see. Thank you.
Okay, thanks.
Maybe this is something that you will mention later, but is it meaningful to ask about non-abelian -1 form symmetry? Is that something you've thought about?
Well, yeah, I mean, the way I have of thinking about this is mainly by examples. And yeah, I don't know any example with that property. I don't think that will make sense, but I don't know, maybe yes.
Yeah,
I don't even know how to think very well about discrete -1 form symmetries. It's something I'm trying to understand. So non-abelian, yeah. I don't know if you have something in mind. But...
No, it's just out of curiosity.
Okay, so let me draw some general lessons from this example. Well, again, this is the definition.
Just one more question. Sorry about that.
Yes.
We go back to transparency just to make sure I understand. This theta could be a theta of a non-abelian gauge field, correct?
Yes.
And so in that context, there's no analog of the Kogut-Susskind pole?
Yes, there is an analog.
So what would that A be there?
Sorry, I didn't. Yeah, I'm going to show this. This A is going to be the Hodge star of the Chern-Simons tree form. So this is going to be the topological susceptibility, the expression for QCD, or for Regiu Yang-Mills, as here FF tilde, FF tilde.
Yes.
Or, well, sorry, so I took two derivatives. So it's like so FF tilde can be written as the derivative of something. So this is this something. Yeah, I'm going to show this.
Mm-hmm. So you're saying that it is the dual to the Chern-Simons of the non-abelian gauge field is the analog of what you mean by A. Is that what you're saying?
Yes.
Which is not gauge invariant. And that's fine for you.
Exactly. That field is not gauge invariant, but the two-point function integrated and taking the limit q to 0 is gauge invariant. So in fact, the Kogut-Susskind, I mean, well, in this, so in the original paper by Kogut and Susskind, and also in the paper by Luscher, they were trying to understand the 4D case, and they used 2D Maxwell as a sort of toy example, but in 4D, the same holds.
Thank you.
All right. Yeah, thanks. Yeah, I mean, this is kind of conceptually the more important part of the talk. So if you have any other question. Okay. All right. So in general, what we will say is that U1 minus 1 form symmetry is spontaneously broken if the vacuum energy, which can be defined in terms of the Euclidean path integral, depends on a constant background field theta. And this can be diagnosed by the topological susceptibility, which is always defined like this. Again, theta equal to 0. I also missed it here. And since star J is a top form, J0 will be the total derivative of something. So it's locally exact, star J. And then I will always be able to write an equation of this form. So whenever I have this topological susceptibility, it will be related to a pole in the 2-point function of a possibly gauge variant function of this form. And okay, I will give an example now, but this non-vanishing of the topological susceptibility signals an emergent description in the IR in terms of a D-1 form gauge field. So in the case of QCD or SUN-Yang-Mills, this will be the Chern-Simons tree form. So this field is not a fundamental field, but we are just so the fact that this pole arises means that there is some IR effect that is related to this chi, and this can be captured, at least in some cases, by an emergent theory of a D-1 form gauge field, which is topological. Okay, so let me, and we will say that this D-1 form gauge field is the gauge field of the spontaneously broken -1 form symmetry, or rather the electromagnetic dual. No? So the Colston should be a -1 form gauge field, but we don't really know how to describe that. But this D-1 form gauge field is the electromagnetic dual of that would-be Colston. Okay. Okay, so let me describe SUN-Yang-Mills. So the action of SUN-Yang-Mills takes this form. According to our definition, there is a -1 form symmetry whose background gauge field is theta. And this is just the instantonic symmetry. And it's well known that in SUN-Yang-Mills, the topological susceptibility is non-zero. And by introducing this K1, which is the Hodge dual of C3, we can write it as the exterior derivative, well, as the derivative of something. And so this K mu is the analog of the little v mu that I wrote before. Then we can rewrite the topological susceptibility in terms of this 2-point function, which in the limit Q going to 0 is explicitly gauge invariant because this quantity is gauge invariant. So non-vanishing of chi signals a pole in this 2-point function. And we say that this implies that the -1 form symmetry is spontaneously broken. And we want to say that the Colston field is this Chern-Simons tree form. This is not so crazy because it's well known that the Larchen, at Larchen, the IR of SUN-Yang-Mills can be described using an effective theory in terms of a 4-form field strength, which is the exterior derivative of the Chern-Simons tree form. And the action at Larchen takes this form. And we just reinterpret this fact by saying that the Chern-Simons tree form is a Colston field for a spontaneously broken -1 form symmetry in the UV theory. You may notice that this theory is the same or the equivalent of 2D Maxwell, but in 4D. It doesn't propagate, again, any degree of freedom, but it describes a multi-branched potential and describes the vacuum structure of SUN-Yang-Mills. An additional check that the -1 form symmetry of SUN-Yang-Mills is spontaneously broken is by coupling to an action. So we gauge the -1 form symmetry. The physics is well known. The action is massive. So this is the Higgs mechanism. Magnetic objects, which are axionic strings, are confined. And well, one can see this magnetic confinement again explicitly by dualizing phi to a two-fold gauge field. There is a Stuckelberg-like coupling. And an important point is that if the topological susceptibility would have been 0, phi would have been massless, in agreement with the fact that we expect the -1 form symmetry to be not broken in that case. So these are all well-known facts about SU and Young-Mills. And away from the large N limit, or in physical QCD, there is still a -1 form symmetry, which is still the instantonic symmetry. The current is the same. It's still spontaneously broken because the topological susceptibility is non-zero. And the low energy dynamics can, in principle, also be described in terms of a three-form gauge field. But the generic action takes a more complicated form. So there is an extra function of F4, which can be arbitrarily complicated, and it's only known in some limits, in particular in the large N limit that I said before, but also in some other limits, as explained in this paper by the Valley that I cited before. All right. Also, this paper by the Valley is important because it made a connection between this low energy dynamics, or this low energy topological quantum field theory, and the strong CP problem. So let me now go to the strong CP problem if there are no more questions about this part. Okay. So the strong CP problem is a phenomenological problem that arises in the standard model. So in QCD, there is this theta, which for us is a background gauge field, which takes values on the circle. So it's an arbitrary angular parameter that arises when you quantize QCD. And experimentally, it's measured. Okay, here, theta bar just implies that I am putting the quark matrix contribution inside. This is the physical parameter. It's been measured to be extremely small. And this gives rise to a naturalness problem because one should explain why an angular parameter takes such a small value. And this is what sometimes goes under the name of the strong CP problem. In our language, okay, so importantly for us, so for the strong CP problem to arise, theta must be physical, so it must enter into some observable of the theory, and this will only happen if the topological susceptibility is non-zero. So in our language, theta is physical only if the -1 form symmetry, the instantonic -1 form symmetry, is spontaneously broken. So this allows us to write a necessary condition for the strong CP problem to arise in QCD, which is that the instantonic symmetry should be spontaneously broken. If one is able to prevent the spontaneous breaking of the -1 of the instantonic -1 form symmetry by either gauging, so if we gauge it, it's still spontaneously broken, but it's not a global spontaneously broken symmetry. So if we prevent this physics by either gauging or explicitly breaking the symmetry, then the strong CP problem is avoided. Okay, we can test this understanding by looking at the well-known solutions of the strong CP problem. The most famous solution to the strong CP problem is probably the axion, which boils down to coupling a compact scalar field to the instantonic current. If one does this, one can absorb the theta dependence in the axion by a field redefinition of phi, which implies that theta should be unphysical. It is now apparent what is happening in terms of the -1 form symmetry. Okay. Also, I should say that this was already understood, not a connection with the spontaneous breaking of the -1 form symmetry, but all this story about gauging the -1 form symmetry and the connection to axion physics was already explained in this paper by Miguel, Irene, and company. Okay, so what we are doing when we add the axion is gauging the -1 form symmetry because we are coupling a compact scalar field to the instantonic current. And well, in other words, the instantonic current is becoming exact, which is the property of any gauge current. And so we see that the axion solves the strong CP problem, but gauging the -1 form symmetry and putting it in the Higgs phase. What about massless fermions? So the second most famous solution to the strong CP problem is just to postulate the existence of a massless Dirac fermion. In such case, there is a chiral symmetry, which is anomalous. And then one can use an anomalous chiral transformation, which is not a symmetry anymore. So it's a phi field redefinition to absorb theta. And then theta becomes unphysical. So that's the way a massless chiral fermion solves the strong CP problem. The equation for the ABJ anomaly takes this form. And what we see is that the instanton current is becoming exact. And so we say that just as before, the axiom, we were saying that the symmetry is gauged. And one reason we would say it's gauged is because the current becomes exact. Here, it also becomes exact, which means that whenever we compute this current in a closed manifold, the answer will be 0. And this is chief property of a gauge symmetry. So we say that the massless fermions gauge the -1 form symmetry. And this is what solves the strong CP problem. This can be, in fact, made very precise in 2 dimensions by using the bosonization dictionary. But in 4 dimensions, this is the reason. Okay, there is another solution to the strong CP problem, which was put forward in a paper by Banks, Cyber, and Dine in 91. And in particular, they discuss a toy model, and then they discuss a 4D example, but I'm not going to discuss the 4D example. In 2D Maxwell theory, there is also a strong CP problem, an analog of the strong CP problem, if the vacuum energy depends on theta, as I described. And this is avoided if one, instead of doing U1 gauge theory, uses a non-compact gauge group R in 2 dimensions. And in our language, we see that the strong CP problem is solved because now R doesn't have, so an R gauge theory in 2 dimensions doesn't have a -1 form magnetic symmetry, because always R gauge theories never have magnetic symmetries. So it cannot be spontaneously broken to start. In fact, one can obtain the non-compact R gauge theory by doing gauging of the magnetic symmetry in U1 gauge theory, but without a kinetic term. And so in this way, we are again solving the strong CP problem by gauging the magnetic symmetry, but in a different way. Okay. Okay, what about new solutions? So all the solutions that I told you so far are just gauging the -1 form symmetry. Is it possible to solve it by explicitly breaking the -1 form symmetry? And what does this mean? So we tried one way in which you could try to break a symmetry is by using mixed anomalies. So if a symmetry has some mixed oft anomaly with another symmetry, by gauging the second symmetry, you can break the first. And for instance, in 2D Maxwell theory, the -1 form symmetry has a mixed anomaly with the electric 1 form symmetry. And you already saw this expression in this talk. And what this means is that if you gauge the electric 1 form symmetry, you should be breaking the magnetic 1 form symmetry, the -1 form symmetry. This can be done by coupling a background gauge field BE and then making it dynamical. The resulting theory is this one, and it's just, the problem is that it's a trivial theory, so it's just empty. There is no dynamics associated with it. Of course, chi is 0, so the topological susceptibility is 0, and the strong CP problem is sort of solved, but the theory that you obtain is trivial. And in 4D, you cannot even do that. So if one tries to do something similar in 4D QCD, in terms of the low energy theory that I wrote before, in terms of C3, there is an electric symmetry, which is 3-form symmetry in this case, that has a mixed anomaly with the magnetic symmetry. And one could try to play this game, but the problem is that the 3-form symmetry is not really a symmetry of QCD, it's only a symmetry of the emergent theory. So it's an emergent theory, an emergent symmetry in the IR, and it cannot be gauged. An open question is whether there are maybe in some beyond the standard model scenarios, whether one can introduce some other symmetries that have a mixed anomaly with the magnetic symmetry, and whether one can use this to solve the strong CP problem. Okay, and then another way of explicit breaking the -1 form symmetry, instead of using a mixed anomaly, is by explicitly breaking it in the UV. So if one starts with a gut theory, say SU5, and breaks it to SU3 times SU2 times U1, in the UV, there is only one instanton number, so there is only one -1 form symmetry, but in the IR, there are 3. And then one question is whether one can try to use this fact by solving whether one can try to lift the pole associated to the topological susceptibility by this UV breaking. One could be hopeful that this can be done because Goldstone bosons, at least for zero-form symmetries, are typically fragile and sensitive to UV effects. So if some zero-form symmetry is spontaneously broken but is only emergent, the associated Goldstone boson will have a mass. This is, however, not true for higher form symmetries. For instance, the photon is exactly massless, even though we think that, well, we know that the electric symmetry is explicitly broken by the presence of electrons, and we also think that the magnetic symmetry is broken by the presence of magnetic monopoles. Regardless of this fact, the photon is exactly massless, and typically people say that the emergent higher form symmetries are exact. So the question is whether an emergent -1 form symmetry, in this sense, is exact. And if they were not, this would be important for us because it would mean that we can solve the strong CP problem by using GATT models. Okay, so there is a toy model for this question. Of course, the question here is very complicated, but one can try to approach it in a simple model. And the simple model is Higgs in SU2 to U1 by adjoint Higgsin in D dimensions. So in the IR, the U1 theory has a D-3 form magnetic symmetry, and in the UV, there is no magnetic symmetry. In 3D, the IR theory, I already explained U1 Maxwell theory in 3D, has a mu, which is a Goldstone, and is the Goldstone for the spontaneously broken zero-form emergent symmetry. And then this emergent symmetry is broken in SU2. So the question is whether a mu takes a mass. Well, in fact, this was described by Polyakov. So in this Higgsin, there are Toft-Polyakov monopoles. And if you take these Toft-Polyakov monopoles into account in 3 dimensions, they are instantons in the sense that they are point-like. And if you take them into account, there is a dilute gas computation that one can do, and the photon becomes massive. So this is as expected. This mu is the dual to a compact scalar field, which is the Goldstone for this spontaneously broken zero-form symmetry. And I told you that zero-form symmetries are not exact if they are emergent. So then the question is whether something similar can happen in 2D. We can take the same toy example. And then the question is whether the photon takes a mass in 2D. The U1 photon takes a mass from some non-perturbative effects that could happen in this Higgsin. In principle, the Higgsin can be done at arbitrary weak coupling. You just choose the scale at which you do it. And the weak coupling expansion can be arbitrarily controlled. And in this 2D example, there are no instantons that can do the job. So in 3D, I told you that the Toft-Polyakov monopoles were instantons. Here in this case, there are no Toft-Polyakov monopoles and there are no instantons. So it's not obvious why the conclusion from the weak coupling expansion should change. And we believe they don't. So we believe that the photon stays massless. And okay, and this would mean that you cannot solve the strong CP problem by changing the UV. We expect this lesson will generalize to GATT theories, but we don't really have a better argument than this one. Okay, let me finish with an outlook. I think I took enough time. So one thing I would like to understand if there is a sharper way in which one can do a Goldstone theorem. I suspect there is not, because there is no Goldstone propagating degree of freedom anyway, but it would be nice if something a bit better would be done. I would also like to understand if there is some more implications to other phenomenological models where action-like fields arise, in particular models that contain monodromy, which is important for the -1 form symmetry to be there. I would also like to understand whether explicit breaking, as I described, can be used in more interesting ways to solve the strong CP problem. In particular, we are working on breaking by monopoles. If you introduce dynamical monopoles, the symmetries are broken. The story is a bit more complicated. This was already described in the paper by Miguel Arinene that I mentioned before, but we are trying to give it another twist. More formally, I would like to understand better what a -1 form symmetry is. In particular, the non-perturbative meaning, if there is some, and perhaps using the SIMTFT, where -1 form symmetry is more naturally formulated, or maybe holography. And a question that I also would like to understand is whether these -1 form symmetries need to be matched under dualities, and whether this has any use. And then I leave you with the rendering of an artificial intelligence of the swamp rangers. Thank you.